In question 4, we have that a capacitor is formed when we put two large plates with equal and opposite charges close together. The question asks us to find the expression for the electric field between the plates of the capacitor and outside of the plates of the capacitor. And a reminder here that electric field is a vector, so we need to include direction. So this is a derivation type question, and we want to show, we want to prove, we want to figure out or derive the result for the electric field. Let's start by doing a sketch of what a capacitor looks like. So here's one plate. I'm going to call that 1. Let's say that that one has our positive charges. Here's the second plate. I'm going to call that plate 2. Let's say that one has our negative charges. If we want to find the electric field in 3 areas, we'd like to find the electric field out here to the left of plate 1. We'd like to find the field in here between the 2 plates, and the field out here to the right of plate 2. That's going to give us complete coverage of finding the electric field everywhere. So let's start by drawing the electric field over here to the left of plate 1. The electric field due to plate 1 is going to point away from plate 1. It's going to point to the left. So there's E1. The electric field due to plate 2 is negative, so it's going to point towards plate 2. There's E2. Okay, while we've drawn these, why don't we go ahead and find the vector sum of these. The net electric field in this area is E1 plus E2. Now let's use the result we said we were allowed to use, that the magnitude of the electric field outside of a charged plane is sigma, that's the charge density, divided by 2 times epsilon naught. So for plate 1, the magnitude of the electric field is sigma over 2 epsilon naught, points to the left, so that's negative I hat. Okay, for plate 2, the magnitude is sigma over 2 epsilon naught, points to the right, so that's positive I hat. The net electric field to the left of plate 1 is equal to 0. Okay, let's get in between the plates next. We'll draw the electric field due to plate 1. It goes away from a positive, so that's to the right. The electric field due to plate 2, it goes towards a negative, also to the right. Let's find the net electric field here. Total electric field is E1 plus E2. E1 has a magnitude of sigma over 2 epsilon naught. It's to the right, so it's plus I hat. Plus E2 has a magnitude of sigma over 2 epsilon naught. To the right, so it's positive I hat. Add these two guys together, we get sigma over epsilon naught I hat. So there's my field in between the plates. Out here to the right of plate 2, my electric field due to plate 1 points away from plate 1. There's E1. My electric field due to plate 2 points towards plate 2 because plate 2 is negative. My net electric field is equal to E1 plus E2. Electric field vector E1 has a magnitude of sigma over 2 epsilon naught. It points to the right, so that's plus I hat. My electric field E2 has magnitude of sigma over 2 epsilon naught. It's to the left, so that's negative I hat. These two guys add up to be 0. Okay, so there's my answer all written on my diagram. Just to get everything nice and neat, why don't we write it out, and let's be careful with that direction, because nobody says we had to set up our capacitor this way. So we'll start by saying outside the plates, E equals 0. Between the plates, E equals sigma over epsilon naught is the magnitude. I don't want to say that the electric field always points to the right, because what if we rotated our capacitor so that the positive was up here and the negative was here? Or what if we flipped the positive and negative plates? Then the field would point this way. So I'm going to say from positive towards negative. Okay, there's question 4 done.